So thank you, Ricardo, for the opportunity to bring these ideas here. What I'm going to do is a lot of the things that I'll be saying is going to be very consistent with what Ricardo talked about in terms of these narrow channels of knowledge and how knowledge flows. But I think what I'll present are alternative ways to sort of make the speed up the process by which these knowledge flows can take place. And these ideas, I'm going to actually basically take you to the edge of what's possible and then push you over from the examples I'm going to provide you. Because what we're finding in our research, both at working with NASA, but also with our medical school, is that there's a lot of knowledge out there in the world, and we just need the right mechanisms in place to find those people and get them to solve the problems for us. With that in mind, what I'm going to start with first is an example from history. Solving a tough science and engineering problem about 300 years ago. And the story starts in 1707 when the entire British fleet sank off the islands of Scilly, just south of the British coast. They had rocks there. They knew there were rocks there. They couldn't find them. And then they lost 3,000 men in this disaster. And so what the Parliament did in the UK is they said, look, we've got to solve this problem. We've got to be able to find our longitude at sea. The smartest guys around can't figure it out, so let's run a prize contest. Prize contests were all the rage in Europe at that time, and they said, let's set up a prize contest. And they put up a prize amount, which even today is significant, 20,000 pounds. In those days was quite large. And what they said is anybody in the world can enter and participate. Sir Isaac Newton, certified genius, inventor of gravity, basically comes in and says that the only way that this solution will be found is through methods of astronomy. And he was actually on the board of the Longitude Prize, and he basically said this is the only way for us to organize ourselves and to solve this problem. So the Parliament, of course, listened. They said, Sir Isaac Newton, go ahead and do your own work, but also we're going to invite solutions from lots of other people. They got a lot of interesting solutions. So there were about over 100 solutions proposed. Some people said, let's just find telepathic dogs, right? And we'll put them on ships, and then they'll bray when they're by the longitude, and we'll know what's going on. Somebody else thought, the ideal solution is to put cannons 100 miles apart across sea lanes. And when it's noon, the cannons will fire, and then we'll know where we're at. And somebody actually thought, well, the best way to do this is actually to set up have a clock, a chronometer that keeps track of time, that actually works at sea. Because when you're at sea, there's lots of motion, there's lots of change in humidity and temperature, and the clocks at the time just couldn't keep track of time. Because if you know time at shore and you know what time it is now, you can triangulate to a longitude. This solution came by this guy, John Harrison. So Harrison was a carpenter up in Yorkshire, and he understood expansion of materials and what happens with temperature. And he used that knowledge to create a clock that actually worked. And they did sea trials, and it worked. It still took 30 years for the Longitude Board to award him the prize because they didn't believe it. But yet, in the end, this was a major discovery, and provided a significant competitive advantage to the UK in terms of its naval prowess. So let me now bring you to today's times, and I'm going to show you another celestial problem that we ran for NASA and solved through a contest. So let's watch this.
Energy, in one form or another, powers everything on Earth, and the man-made things floating above it, too. This is the International Space Station. You've probably heard of it. It's powered by the sun, and the sun's energy is captured by the station's solar panels. Ensuring the space station harvests the most energy possible is a complicated task. Well, for one reason, see those large solar panels? Holding them to the station are very long, thin arms called longerons. Anytime an odd number of longerons are in full sunlight, with others in the shadows cast by the rest of the space station, they bend and eventually break. For this reason, ISS operators are careful to position the station to limit shadowing, and so only an even number of longerons are shadowed at one time. However, this conservative positioning reduces the power the station can collect from the sun, thus causing inefficiency. NASA wants more power for the ISS. More power means more science and cool stuff that NASA can do on orbit. NASA needs a sophisticated algorithm, and they think you just might be the key to this whole equation. Introducing the NASA Tournament Lab International Space Station Longeron Challenge. Your solution just may help power the International Space Station and allow more science for more scientists around the world. Consider this your invitation to blast off with NASA. For more information, visit topcoder.com/ISS if you've got the right stuff.
So unlike the kayak, we actually know how the space station works, right? So we actually have the science behind it. It's very complicated. And it's kind of ridiculous, actually, that NASA would say, we're going to go to any random person in the world and ask them to suggest a solution for us. But that's what we convinced them to do. Here's what we found. This was a 3-week-long contest. We had 459 competitors from around the world, 2,000 code submissions. The winner, this is Italian, Chinese, Polish, Chinese, Belarusian, Canadian, Chinese, Estonian, okay, in terms of winning. And if you think about the prize amounts, there, it's like basically a first-class ticket to, to the UK, basically. So not that much in terms of prize amounts. And what's interesting also is the performance. So what I'm mapping here is the output that their algorithms provided to us in terms of the solar power and kilowatt hours. What you see was very interesting is that a lot of the competitors are pretty close by. There isn't that much differentiation. We run these winner-take-all contests, so even a 0.001% difference will make you successful. But a lot of them are very close by. But what's shocking is that this is a solution that Boeing provides to NASA right now for $25 million a year. All right? So, and none of these kids, had any background in astronomy or astrophysics or whatever. And so this is part of this conversation as to there's a lot of latent knowledge in the world available if we can match those folks with the problems that they could solve. And even though you might be specifically focused in one particular industry, there's an ability to come up with an abstraction of the problem so that that knowledge can be unlocked and put to work on that problem. So why do we care about these elements? And why am I sort of talking about this? The first element here is that when it comes to innovation, when it comes to R&D, there's just a tremendous degree of uncertainty. In fact, many would argue that becoming successful in innovation is a random stochastic process. And so this is Charles Kettering, co-founder of General Motors, in testimony to Congress, basically saying that there's just, you don't know if you're going to get the thing, if it's going to have any value whatsoever, and when it'll arrive. And if you talk to anybody doing any kind of R&D or product development work, they would agree with this perspective. The second perspective, which is known as Joy's law, is that no matter who you are, most of the smartest people work for someone else. Now, at the Harvard Business School, when we do executive education, this is anathema, right? Because the CEOs say, come on. Like, I know how to hire the best people. They work for me. But if you just do the math, in any kind of a situation, in fact, what you'll find is that there will always be more people who have knowledge on the problem you're trying to solve outside of your firm or your organization than inside the firm. So you have a labor market problem. But also what's interesting these days is that our models for organizing creative effort are also changing as well, and radically so. So how many of you guys grew up with this in your homes? Anybody know what this is? Yeah, Britannica? Great. And you've bought Britannica for your kids? No? You did? Ricardo did? Okay. What's happened to Britannica? Well, in between Britannica, there was Microsoft Encarta. You guys remember this? Right? Encarta was there, and what this did is it changed the model from door-to-door salespeople and a 10-year refresh cycle to Best Buy and a 1-year refresh cycle, basically. How many of you have used Encarta recently? Yeah, because everybody is here at Wikipedia. And Wikipedia is interesting. How many of you guys were on Wikipedia in the last month? Okay, good. All right, good. Last week? Okay, good. All right. I won't ask about today. Wikipedia is interesting because it's a natural shift in the distribution. You go from books to CDs to the web. Makes a lot of sense. But what's radical about Wikipedia is that there's nobody who is actually in control of the content being generated. Anybody anywhere in the world can submit an article, can submit a little stub, can change the grammar, and it works all the way from bottoms up. And in a decade's time, this is dead, and this is now the standard by which all of us access knowledge about the world. And some of us maybe even be contributing to it. And that's a radical shift, right? If you think about hundreds of years in making for this, a few decades of making of this, and now this is all over. So I'm going to run slightly over time, so I'm just going to power through it. So what is behind all of this? What we know is that when it comes to innovation, what we care about are extreme values. So for whatever dimension of value you care about for innovation, what you care about is finding the most extreme value in that dimension. And if you assume that the outcomes for innovations are normally distributed, what you have to start thinking about is, if I just have one team or one person or one company trying to solve this problem, most likely what you're going to get is actually the average, right? If you think about Stats 101, if there's an underlying distribution of outcomes, the first time you do something, most likely you're just basically going to draw the average, right? And it's only through multiple independent trials will you actually get the entire distribution. And that's what crowds enable us to do. Crowds put into motion a perspective of lots of independent trials so that we can, in fact, find the right solution. And you can organize crowds through competitions, through contests that I gave you an example of, or through communities. And communities also can be set up in ways in which you can get multiple independent trials for the problems at hand. And I want to give you proof positive about this, about Joy's law applying to the medical school. So just as across the river, there's always sort of a lot more hubris, about who the smartest people are. So we ran an experiment with the medical school folks in the area of big data analytics and genomics. And the question was, could we, for $6,000, solve a long-standing problem that one of the researchers was having with genomic sequence calculations? And we said, can we do this? So we ran this contest, and here's what we discovered. Again, similar to what you saw in the Longeron challenge, lots of people participating, lots of submissions, and also lots of diversity in the solutions coming through as well. So not only do we get lots of numbers and lots of attempts, but lots of different approaches to solve the problem itself. Winners came from Russia, France, Egypt, Belgium, and US. And we could do a lot of calculations very fast. But what you want to know is, compare this to what? Like, how good is this compared to what? And what I'm going to show you here are the scores deconvoluted into two dimensions. There's time, which is how fast can you do this, so you want to be on the left side, and how accurate are you, so you want to be on the top left side here. The green dots represent the submissions from our developers in this contest. The yellow dot represents the solution from the Harvard researcher who has a lab working on this problem for about a year. Okay, this is a log scale. And then the red dot represents the solution from the NIH. Okay, none of these guys have any background in computational biology. Okay, again, what we did is we took the problem, abstracted it out of its genomics gobbledygook, and made it into a math problem, and then we had these guys from Belgium, US, France, China participate and solve the problem for us. All right? Again, we see the same thing. There's now platforms available which enable you to run contests and communities on demand. I'm not going to give you all these details, but we've done a lot of work with NASA on this kind of stuff. Just one element to sort of look at, again, is the number of people we can attract. NASA attracts all the best nerds in the world, and basically when you put up a really cool problem, you get lots of people expressing interest and lots of submissions. And that's in the project rooms column here and the submissions column here as well. And what do we know from our analysis of these contests? What we know is that basically people at the margins of knowledge, margins of society are the ones that end up winning in these contests. So all these contests are run double blind. You don't know who's submitting, and you don't know who you're submitting to. Evaluation is done double blind as well. And what we found in our analysis is that people that are further away from the problem domain are more likely to win than those that are close to the problem domain, because they're just not encumbered anymore with the constraints of how to think about the problem. And then also, women tend to win more than men, and there's lots of reasons behind why that may be going on too, but I won't, you can read the paper to understand that. What I'm going to show you actually is how this all can come together. So here's an example of a company called Local Motors, which is putting all of these elements together and making cars. They're out in Arizona.
This is Local Motors. Welcome to the Forge, empowering a community of designers, engineers, fabricators, enthusiasts who are passionate, supportive, informative, inspirational. Community of give and take on a mission to accelerate vehicle development. Open resources. Size doesn't matter. No idea is too small or big. Engage the Forge. Start with an idea. Sketch it. Snap a picture. Upload your work and showcase it to the world. Meet experts. No, more like these experts. Evolve your idea. Get the tools you need. Get feedback. Improve your design. See it come to life. Make awesome real. Join a project. Give feedback. Contribute. Maybe compete. Get recognition. Or this recognition. Or even this.
We found a small company in Arizona called Local Motors.
Be a part of something huge. Be a member of the Forge.
So if we go back to the example of the kayak, what's happening is that kayak took a long time, long process for it to evolve. And what we are living in a world now, especially with digital technologies, is that the same processes can be sped up. And in fact, they may be actually better sped up on the outside of the organization than inside the organization. The car you saw, the Rally Fighter, was developed completely through the community. Engineering, development, design, every single element was done through the community. And more than 400 contributors from around the world participated in creating that car virtually. J.E. Rogers' company put it all together at the end, but that whole design process, the whole engineering process was all done on the outside world. And this is what basically enables us to sort of think about unlocking those channels, those very narrow channels, by going out and putting ourselves out there instead of assuming that it'll all come to us directly. You know, by contract, I have to show you a 2x2 because that's what we do at HBS. It's in my dean's in my contract with the dean. So what I'm going to show you is a very simple 2x2 to sort of think about how all these elements come together. So one perspective is what I sort of showed you was the knowledge required to solve a problem. Right? For any problem, you know, is the knowledge held narrowly in a few people or is it broadly distributed? And then also, part of innovation is not just generating knowledge, but also selecting amongst those various different innovations. A gentleman you heard mention about the fact that lots of combinations can be crappy, and you need to be able to select amongst the best combinations. And that also is knowledge that could be concentrated in one person or very broadly distributed. What the default is of internal R&D is that we assume that the knowledge to generate the ideas and the knowledge to select amongst those ideas are within the organization, within the firm, within one team. But what we can see now is that with declining communication costs and modularity, that in fact, we can now think about ways in which we can allow more people to select. So consortiums are one way where a few people suggest ideas, but many more people get involved in selecting amongst those ideas. And the internet came about because these consortiums existed. What I showed you of contests and prizes, where basically lots of people come up with ideas, but a few people end up selecting them, or you automate the selection process. Or the world that we live in today of open source software communities and threadless, where basically both the generation of knowledge and selection of knowledge is broadly outside. This is where the world is going to. This is where we're at. And what's interesting is that we have all these options available to us. They're not competing against each other. They can be put to use together. But the focus always tends to be is let's do it all ourselves. And what we're showing now and the data that we're putting together are both what the mechanisms are that enable all these things to come together, but also how companies can actually partner with the crowd instead of think of them as substitutes. Okay, I'm going to stop here. Thank you.